Good morning, Professor. So this is my assignment. For the first item, I first tested the assumptions given in the table in the laboratory number 6. So the assumptions are on the assumptions column with positive and negatives. Then I did the Pearson correlation on the continuous to continuous variables for Ellen Price as a target. Then for the categorical variables, I did the point by serial correlation. I think that is the last three here, or no, the last four here. These are categorical variables, so I use point by serial correlation here. So in this assumption, comparing the correlations and assumptions, uh, all of the assumptions are supporting the correlation values that I have computed using Python. Then for the so this is the original OLS regression result. Uh, so the R squared here is 0.94, which is fairly high. However, our p-values here are mostly zeros, and others, the ln ceiling is 0.95. So on the notes here, uh, there is a strong multicollinearity, or there is an assumption of strong multicollinearity among the variables. So supporting that with item.
Let me see the notes. The notes over there is from the output.
Yes.
Okay, so Python
Yes.
show this one to you.
Yes.
All right.
With that, Professor, the item number 2 for multicollinearity concerns. So this heat map, or this figure right here, shows the correlation coefficients of the continuous to continuous variables. So as you can see here, most variables are highly correlated with each other than our target, which is ln price. And ln h is, sorry, I had a call on my phone. ln h is negatively correlated, or highly negatively correlated with uh, most of our variables here. Then for the VIF computation, Professor, I did the auxiliary regression. So 5 of the regressors. Uh, 5 of our regressors here have high VAF values, while the other half, or the other 5, has below 5 VIF, or variance inflation factors. So what we could do here is try to limit the use of these variables, or do some pre-processing in order to the computation for the VIF, Professor. I used the formula that you gave last time. Yes, Professor. Then for the I use Python to show these numbers, Professor. But the VIF function of Python is different from the equation that you have given us. It's the same. But some the different results. Mm. Oh. Okay.
Values do have center and uncentered, right? So we are using centered VIF.
No.
Okay, and above 5 is you made it
Yes, Professor.
Okay, okay.
This is
And I'm really interested in what Python is really can automatically make some comments or the tables, like the one you showed that,
uh,
the notes 1 and 2, which is really out of.
yes, Professor. Uh, then for the heteroscedasticity concerns, Professor. So first, I used scatterplot to visualize the relationship between the ln price and pass. So as you can see here, there are some, or it's imbalance, and there is no linear relationship at all with the ln price and the pass. So this kind of gives us a hint that something is going to be uh, analyzed further for the succeeding steps. So with that, Professor, I used this is another automatic plotting by Python. So as you can see here, Professor, I'll just focus on the residuals versus pass. Uh, for 2.0 and 4.0, uh, it's not actually very much seen here, but uh, it's like an opening fan for from 2.0 to 6.0. So that indicates a heteroscedasticity concern, given that the values for 2 the residuals actually is lower than 4, and 4 is lower than 6 for their values. Then conducting the BP test, these are the null and alternative hypothesis. So if the p-value is uh, greater than, oh wait, oh, huh, huh, uh, 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 yeah, yes, Professor. So I used Stat Models API. It's another tool from Python. Let's just move to the table. So it gives us the Lagrange multiplier statistic, p-value, f-value, and fp-value. So most of the p-values from the PV test is less than 5%. So that suggests heteroscedasticity. Then doing the white test.
Oh, yeah. You want to say something, Rachel?
Actually, I want to ask, does the regressor including the LN price for the BP test?
No, no. But I just start. I did a for loop there, or a looping statement that includes every variable. So I think I should remove this one for the BP test and also the white test. I used Python, Professor, to automatically compute the values here, but I just gave him, or gave the condition that all of the variables from, or all columns will be used as regressors. Uh, yes, Professor. Well, it automatically computes the Lagrange multiplier. That's why I just included it here. But the results focuses on the p-value, f-value, and fp-value, Professor.
Well, when we say the BP test, we wanted to show that the model itself does has heteroscedasticity problem. So so it's using n times r square, and which is chi-square distribution. I don't know what is this. And how can you use each one of the regressors and show the p-value?
Uh, I used this
What is
function.
that?
It's a Python library professor or function from the stat models library. So I just used or created auxiliary regression models, professor. Then the results are then inputted or input in this function, which is
And excuse me, Dylan, did you use the Python to do this one? Yeah, sure, sure. So maybe something, you get
I missed the step, professor.
yeah. So this is not what we we do from BP test.
Okay, understood, professor.
Maybe this is, like you said, it's auxiliary regression. So
And
which is something like, multicollinearity problem.
okay. So then I'll just skip to the estimation and re-estimation for the heteroscedasticity corrected errors. So
Excuse me, which step are you?
wait,
So you're finished the BP test,
let's
which is step 4.
yes, and 5 I also did the
Step 5 is Y test.
Y test, professor. However, I just got the p-values here as well.
There's something wrong. This is wrong either.
Yes, professor.
2.
I will look into it, professor. Then there's just a pair plot.
Now get to the step 6, which is equation estimation.
Yes, professor. So this is the I placed the original model again here, professor. Then used the robust model here
Mhm.
for re-estimation.
Yeah.
So in order to see clearly what is the difference between these two, I created this table with
Okay.
the original and re-estimated values. So the only similar results
Uh-huh.
is
R squared.
r squared, and the coefficients here or the values here are not equal to each other. Then
Which one is larger? Which
uh,
one is smaller?
it's here, professor. So in table 6, uh, I compared the original and re-estimated value. So who is the larger one? So
Oh, you mean this is the coefficient comparison.
yes, professor, the standard error
And
comparison.
the above there is the standard error comparison.
This is the coefficient comparison, professor.
This is coefficient.
Yes, professor. Yeah, this is the coefficient.
But according to this heteroscedasticity corrected standard errors, they should have same coefficient, but different standard error. Isn't that true? So
For my results, professor, I think no. But looking at it closely, some values are close to each other. However, some
no,
are not.
it should be exactly same
So
for coefficient, but standard error is different.
oh, okay.
So what's this? This one seems to be no, I mean the lower one. This one seems to be the coefficient estimation. Look at those numbers, exactly the same. So this is the coefficient estimate, and the upper one is standard error.
Oh, maybe I flip the.
Do you have the same answer as
Ah,
what he did for the estimation, coefficient estimation? Is this the same one? No? Well, The number is different. How different? It's so far away, or just 4 decimal or 3 decimal places different? I think this is the coefficient estimation. Yeah, this is coefficient. Do you have the same? So it's actually totally different. Yeah, some of the coefficients should be negative, but what you show it here, everything is positive.
Wow,
But
maybe.
originally, if we do the OLS estimation, some of them is negative.
I think something might be wrong with my code in Python, professor. So,
Yeah, maybe
give.
your coding is.
Yeah.
That's the problem of writing the computer program,
Yeah.
right? If your command is wrong, then everything is wrong.
Yes. So with
Okay.
that, professor, still with the results, somehow it did not improve with the re-estimation.
Oh,
Um,
it doesn't improve?
yeah, it did
Oh,
not improve.
well,
So,
that's.
one thing looked into was, since all of the values in the data is on natural log, so I think we could put it back to its original value and try to do OLS there, uh, and check if the results would be better. But I have not done it yet with Python. So I think that's one thing we could do to improve the OLS model for this activity, professor.
All right. But actually, there's a lot of mistakes in these reports. Okay. Who will be the next? Uh, either one of you will be the next. No, we just take turn for these two program students. Okay, so, okay, excuse me. So, here. Make it a little bit larger. Sorry, my eyesight. Okay.
Hello? Okay. LM price is the R dependent variable, and beta 1 we think is positive, beta 2 is positive, beta 3 is positive, beta 4 is negative, beta 5 is positive, beta 6 is positive, and beta 7 is negative, beta 8 is negative, beta 9 is negative. So formula will be like this. Oh, there's one more E. Okay, so this is the result. Wait, where's the question? Okay, so the question is, use LM price as a dependent variable, and to find which variable have coefficient that's significant in expected direction in a 5% level. So the result. Okay.
All right.
This is the result. The all the other signs are the same except the first one is negative, which we expect to have positive. And but if you look at the probability, you can tell that this variable is not significant enough. Instead, with 5%, beta 2, beta 3, beta 4, and beta 5, beta 6, beta 7, and beta 9 is important. the only two the only two variables which is not significant enough is beta 1 and beta 8. Yeah, so here's the result. Here. Okay, the second part, multicollinearity concerns. So this is the pairwise result here. And I spotted that from beta 2 to beta 6, they have the pairwise result which is higher than 70% here, as you can see. And here also with this one is beta 1, so which include from 1 to 6 actually. And here's why. And if we look at the VIF again, you can tell 1, 2, 3, 4, 5, 6. They all have some amount of center VIF, especially for beta 2 to beta 4. It's more than 5, which is the standard we use. So VIF show that these three variables are highly suspected with collinearity problem.
Okay.
And so the step 3, heteroscedasticity concerns. The result is like here. Okay, so I was confusing with the question. Plot the residual from your OLS regression. So I'm guessing is that we only focus on the path variable, the passenger capacity variable. So the result I do is from eViews, when you pick on the regressors of BP test, I only pick paths instead of all the.
Oh, okay.
But I still use the same model, the original
Okay.
model. It's the same
Sure.
model as
Yeah.
as here.
Yeah, here it shows the plot, the residuals from your OLS regression against passenger capacity.
Yeah.
So you should plot.
So
maybe-
it's a picture. Should be a picture.
Yeah, there's a graph.
Okay.
Okay, after you run the regression, then we will have the variables called residual. The residual always stores the updated regression models residual. Okay, then you can name that. You can generate a variable from that. You know, you are not able to use that original we have the variable. Can you show the variables? Oh, you don't have that. Okay, never mind. No, if you run with the eViews, then automatically they have some variables. One is C, means constant. The other one is RESID. That's called residual.
Oh yeah.
Okay, whenever you run the regression models, then you the models will generate residuals, and that updated regression model residual was stored in that variables called RESID. So if you're going to use that variables, I mean the data from the residuals, you need to generate a new variables. So using the generate function, then you give the names for that residuals. Maybe you call residual 1, RESID 1, equal to the original RESID. Then using RESID 1 to plot the diagram.
Oh, okay.
Okay, this is how we do. Maybe I didn't teach did I? I think I did it maybe last semester or something. I forgot. Just one time, okay.
Did we do the plot in last class?
E-views,
Oh,
okay. Can you show it later on? Did you put that graph?
I was going to ask.
Did you show that graph?
I mean,
No,
did
no,
we
okay.
teach about that in last
Okay, I'll
class?
show you next
The
time.
plot. The step 3. Yeah.
But never mind. Your plot is based on the Python or eViews? Well. I'll show eViews
Oh,
after this presentation, okay?
Okay.
All right? And so this one you should plot the residuals based then using passenger variables as an x variables, then the residual as a y, then do the plotting. Then you will see. I think I saw John's one of the graph related to the past. Yeah, that one. Similar like that one. Okay, then you will see that according to the plot, there are some patterns, means heteroscedasticity problems. Okay, so this is your BP test using pass, the variable pass only to do the BP test, right? Okay, that's fine. That's fine since you know this one. It seems to us that we just suspect this word, these variables. So you can do that way too, or you can do hold the models just like the textbook shows.
Okay.
Okay, so either one is, I think it's fine. So according to this result,
Yeah, the chi-square is 0.02.
yeah, so it means, what does that mean?
If we set the significant level as 5%, then it will have, then it is a there is a heteroscedasticity problem. But if we set it to 0, then
What do you mean by set it to 0?
depends on the confidence level of chi-square, like the standard.
This is called p-value approach, right?
Yes.
So when we do the p-value approach, what numbers do you have to compare with your p-value?
Usually it's 5%.
Yeah, so what did you do?
Oh,
Why did you use 0?
Oh, I use 0 because the original formula is because we have to equals to 0. But if we
No. The 0
substitute.
means coefficient.
oh,
When we do the
okay.
non-alternative hypothesis,
Ah.
that's the 0 is coefficients. That is
okay.
not p-values.
Ah,
Oh,
So here
really
should be-
have to careful.
Wait.
Okay, if we use p-value approach, always compare p-value with alpha level, right?
oh.
So this is 0.05.
So it should be like this.
No, 0.05.
Oh yeah.
So since it is smaller than alpha, then
There will be heteroscedasticity.
yeah. So actually, it's reject the null hypothesis, right?
Yeah.
Okay.
So there it means that there's a heteroscedasticity.
Really has heteroscedasticity problems.
Okay.
Okay, all right.
And then step 4, use all the right-hand variables to run BP test, and using 5% level. So
Okay,
the-
actually, step 3 is just like looking at a plot,
Oh.
just by looking at a graph
and step 4 is
to
looking
yeah,
at the data.
instead of just do the BP test according to the problems. But since you do it, that's fine too. Okay, but you don't have graph.
Yeah.
Okay. All right. So step 4 is the original VP test that we run it.
And the chi-square here is 0, which is which means there's a heteroscedasticity problem,
Yes.
and the formula is like this. So that's the same. Do not reject the new hypothesis. Wait,
No.
reject reject the null hypothesis. So the residual will.
Yeah, you should reject.
Yeah. Okay, so here it should be reject. Yeah. Should be like here.
Reject
Yeah.
and do not reject is the reporting conclusion, although it's the start and it's the beginning of make the conclusion.
I was kind of confused.
Yeah, okay.
But the result here is correct.
Yeah, that's right. That's right.
Yeah.
So, but it's conflict, right?
So, did I wait? So this one is correct.
Yeah, but the alternative hypothesis, at least the 1 alpha j not equal to 0. Alternative, At least the 1 alpha j not equal to.
Oh, that's why. Oh, okay. Here, like this. Okay. Okay. Oh, step 5. Test the regression in step 1 at the 5% level for heteroscedasticity using y-test.
Mm-hmm.
So the result for y-test is here. And the question is how many variables on the right-hand side of auxiliary regression? There's
how many?
According to chi-square here, there's a 46. And what is the chi-square critical value?
Chi-square, we call it
Oh,
chi-square, it's not chi-square.
Oh,
Okay,
chi-square.
chi-square. But
Okay.
nobody knows what's chi-square.
Chi-square.
Chi-square, okay.
Critical value. And according to a y-test, there appear to be a heteroscedasticity in the
Mhm.
model.
So look at the huge.
Yeah, these are all the results.
Huge, all right, okay.
And the R square here is. I don't know if the R square here is important or not.
Well, that R square is using, look at the upper. We have this R square, right?
Just the R square.
Yeah, then go up. Then go up again. Then look at this one.
Yeah.
Using observation times R square.
Uh-huh.
So how many observation do we have?
195.
195. So using 195 times the one you just have at R square,
Yeah.
then you get those numbers. You get these numbers. You get these numbers. And based on these numbers, the probability using chi-square distribution is 0. It's near
so
0.
It's important. Okay.
It's important. That R square, from that R square times 129, then come up with these numbers.
Okay. I see.
Okay? All right.
So 46 variables, as I mentioned, and probably chi-square is very close to 0. And according to a y-test, there's a heteroscedasticity problem because chi-square is equals to 0. And here again, should be reject null hypothesis.
Mm-hmm.
Okay. So step 6, re-estimate the model in step 1 with heteroscedasticity corrected standard errors. So the left-hand side one is the original one, and the right-hand side one is the corrected one, as you can see here, white standard error covariance. And so the original one, the difference here, as you can see, the coefficient are the same.
Exactly
the
the
same.
same,
Yeah.
right? But the standard error,
Yeah, but the standard error has slightly different, and the t statistic it has a slightly different because of standard error, and
Yes.
therefore the probability is different too. And I spotted this one, LM fuel, have the most significant change because here if we just look at the probability part, there's not much difference between these two, but for LM fuel, since our confidence level is at 95%, which is alpha equals to 5%, it was significant, but after the correction, it became not significant.
But this is one-sided test, remember?
Yeah,
We have the expected signs.
yeah.
So this one-sided test, and the probability here is two-sided.
Oh, we should divide it.
We should divide it by 2.
Oh. Well, then
Remember that?
it's still
Always
if-
remember that.
It's still if this
Okay,
significant.
but it's still significant is
Yeah.
2 star sign and 1 star.
Well,
Yeah,
then
this 1 star sign and the other one is, it's 2 star signs because they're all between less than 5%.
and for WTOP is still insignificant
Okay.
because it's still more than 5%.
What did you see from the standard arrow? I mean, the number of the standard arrow.
Some of them increase, some of them decrease.
Yeah, that's important. You know, not always
Decrease or increase.
decrease or increase. Some of the variables increase, some of the variable decrease.
Okay.
Okay. All right. That's it, right?
Okay. There's step
Oh.
7.
Yeah, just comparison.
Yeah.
You already compared it.
Oh, okay. So
Anything what you want to say?
yeah, a little bit more. It's for beta 1, 2, 5, and the last one, it increase. The
Oh, okay.
the standard arrow increase,
Mm.
and the question here is doesn't this make equation worse? So in my opinion, solving the heteroscedasticity problem is more vital than the slightly rise of the standard arrow. So
Mhm.
I would I would still solve the heteroscedasticity problem first.
Mhm.
Yeah.
Okay.
That's
All right.
so,
Okay. Thank you very much.
thank you.
So won't be the next in this electrical engineering group. Yes. Wanted to be the next. Okay, so Dylan will be the next, and you use your computers. Okay. So, what should we do here?
I checked last time that I presented. It's still recording. It's
Okay. So do, yeah. So, you don't have to sit here. Do you need to? Yeah, you need to connect that stuff. Those techniques. That is my so using this microphone. Okay, all right. It's always interesting to see the different program runs the same questions.
Hello, Professor. So I tried to do my homework again with Python. So this is my notebook. So I just tried to get the data first in a way in CSV. I converted the data to CSV. And here, actually, this is the libraries that I've been using to check for heteroscedasticity. This is the white and the BP test. So this is the other one that I used. So yeah, this is just getting the data, all of the 195 data points. I just tried to explore the data here using different plots so we can see if they have linearity. Here we can see here there is linearity. Just for initial exploration of the data. Then for actually skip to step 2, then I'll get back to step 1. So for the multicollinearity concerns, I just did some Pearson correlation, and we can see the red parts are where's the heat. So we can see that there's very high correlation between these parts. So from Ellen Price to pass, we can see very high correlations. There are also high negative correlations here with the price and the age, and yeah, so that's one outlier there. But most of the multicollinearity parts are suspected here from the ceiling, cruise, horsepower, fixed gear, and fuel, and passengers. So that's something that we might need to watch out for later.
Okay, I like to mention it again. When we see the multicollinearities, always just put the x variable only.
Oh yeah.
Do not put the y variable.
Yeah, yeah, yes.
So here, the log price is a y variable.
Yes, yes.
Okay, so always put the x variable only because not multicollinearity problem exists among x variables.
Yes. Okay. Yeah. I'll keep it.
Okay, always remember that. Okay. Okay.
I actually skipped in this part, Professor. So I did a regression down below, then put it back
Yeah.
here.
Okay.
But I just did an auxiliary regression, then computed my VIF, and this is the results. So this is only for the x variables. So we can see here the one with the suspected multicollinearity
Yeah.
is cruise, horsepower, fixed gear.
Yeah.
These are the VIFs above 5. Also, but we do have pass here that is very near 4.5. But this is something for consideration, Professor.
Yeah. Okay.
So next, I'm gonna go to the heteroskedasticity concern. So this one, I tried to do the regression OLS again, and this is the results. So we have R squared of 0.94, and you can see that our p-values here, and we can see ceiling is a very high p-value, and yeah, that's for just the regular OLS. And again, we still have the notes here. I just got the standard errors, extracted it from the model, and I could see I just got it in one separate array or vector. Then I got the residuals also. I put it in another spreadsheet. Then I did a categorical plot. I actually did the box plot together with the
Oh, okay.
passengers. So
Okay.
we can see the increasing variation
Okay.
from 2, 4, and 6. These are the categories. So they're now increasing values. So we can see this. This is a different, my interpretation. But I did
Okay.
see a different plotting in eViews I tried to explore last night. So
You mean the graph?
I don't know if it's the graph that we want, Professor. I didn't put it in my homework, but because I just explored.
Yeah.
Yeah.
We can use this one in the eViews too.
Oh, I didn't know.
eView.
Oh, this is a box
Box
plot.
and
Box and whisker.
box plot. Yeah.
Oh, okay. Let me explain.
Yeah, explain it.
So in the box and whisker plot, so we have, this is the box and this is the whisker. So you can imagine this instead is a top view of a Gaussian distribution. So the middle part here is the mean. This is the center of the graph. So if you have something like a Gaussian, the peak would be this line. And this would be on your standard deviation. And this would be for the other quartiles. So you can see like a top, it's like you're comparing different distributions for each. The diamonds would be the outliers. So here we can see that there would be increasing standard deviations.
Wait, let me explain more about the box plot, okay? You all learn statistics in undergraduate? Huh? You do, right? Okay. Usually this box plot, we learn it is for undergraduate statistics. Okay, so let me say it again, okay? In the middle parts, this one, this two looks like middle, right? And this one definitely is not middle, okay? So I'm saying that the box here, this is the bottom line, the bottom box is 25%.
25%.
And this line will be 50%. I mean the data, 50%. And this one will be 75%. Okay? Okay? Then this two, this is called whisker. This is called whisker. And this one, oh no, this one will be, look at there's one with the diamond. means after you have this box, okay, we have what we call interquartile range. Interquartile range means the difference between the, this one is 75%, we call it Q3. This is Q1, 25%. And this one is Q2, 50%. So interquartile range means using Q3 minus Q1. Okay? Q3. I mean, this numbers minus this numbers. And times 1.5. Times 1.5. So this is the length of that length. Okay, for example, if I have IQR, you know, just say, I'm saying this one. Do we have ink here? Okay, if I have Q1, Q2, Q3, okay, something like 10, 15, or 30, suppose, okay? So IQR will be using 30 minus 10, so it's 20. Then IQR times 1.5 is 30, okay? So using Q1 minus 30, so which will be negative 20, okay? Then Q3 minus 30, so Q3 mil, oh, this example is not very good, but look at that, this is what I'm saying, okay? So make it 40. Okay, so if this is 40, then this will be 30. Okay, 1.5 is 45. Okay? All right, so Q1 minus 45 turn out to be negative 35, right? Q3 minus 45 turn out to be negative 5. It's negative 5. So this one, oh, this is positive. Is this one? Oh, this is negative. Okay, again, all this is negative, okay? So you draw this Q1. This is called the limits of Q1. And that one, the upper one, will be the limits of Q3. And whatever the original value outside this two will be outliers. So for this one, for this number 4 passengers, there's one outliers. But for 2 and 6, there's no outliers. So this means something really have different. So if you see the graph, you will see, I think I saw the graph from John's, when passengers equal to 4, which has some, it's a bigger difference or something like that. So so the graph, box plot is one of the graph, visual, useful graph, and origin, this one. Okay,
So
this is the
another one.
another one.
So these are categorical plots, Professor. So
Okay.
the other one is I just changed the kind to box.
Oh,
You
okay.
can actually change this to the violin one.
Okay.
It's really weird though.
Yeah, and looks one. Okay, can you see the original dot one? No, although it's always hard to tell the story or information from the graph,
Yeah.
you can see that from 6, it's really widespread. Okay, and there's something wrong here, for the past equal to 4. Then 2 is something like this one. So the variance, it seems, a little bit increase as the passengers, the number of passengers increase. This is just how we visualize from the graph. But we all like to see the scientific numbers, which is more correct. Okay? All right?
Okay.
All right.
So next, Professor, I'll be doing the BP test. So this is, in Python, this would be just the only BP test that we'll have.
Mhm.
Just zoom a bit. So we just put the residuals together with the exogenous values or the variables.
Mhm.
Then this would be the interpretation. So the first one would be the test statistic, the chi-square, F statistic, and the F p-value. So using the BP test, we can see that the chi-square is 1.27
Yeah.
negative 0.5 raised to 10 times raised to 0.5. That's very,
Uh-huh.
very low. So that
Uh-huh.
means it's
Yeah.
very less than 0.05.
So is this the one match with our result?
In
No,
eViews, I think,
this
Professor.
is BP test. Is it?
The BP test in eViews will show 0, Professor. This one is very so much 0.
Oh, since this number is also very small.
Yes.
Yeah, okay. All right. So it's sort of match.
Yeah.
Okay.
Then for the white test, Professor,
Mhm.
just change the function to from the Broish pagan to
Okay.
white.
Yes.
The chi-squared is really small. So this one is on the negative 0.9 exponential. So it will show 0. So in this case, we reject the null hypothesis since the chi-square is really less than 0.05. So there is heteroskedasticity in the data set.
Well, actually, is this the p-value from chi-square? I mean, is this the p-value from chi-square, or is
yeah.
it just chi-square values?
It's the p-value of the
Yeah,
chi-square.
it is the p-value from chi-square.
Oh,
So
this
this
is
one
wrong.
is not chi-square.
Oh, it's
This
not
is chi-square.
Oh, my label is wrong.
Okay, so you have to say the p-value of this chi-square less than 0.05.
Okay. I just labeled it wrong, Professor.
Okay, so this is test, the statistic.
Mhm.
So this is the number we showed chi-square here.
That's the chi-square.
And this chi-square
Chi-square.
test, the statistic, the p-value is this. Yeah, this is the chi-square value. I think your eViews shows these numbers. So this is the chi-square value. And
Okay.
with this chi-square value, the p-value is this.
Okay.
And if you use F statistic, this is the F statistic, and this is the p-value of the F statistic. There's another way using F test, but here we're talking about this is using chi-square. And both of them is okay. It's okay.
Oh, yeah, I just labeled it wrong, Professor.
Yeah.
But the results would be still the probability of the chi-square.
Yeah, that's the p-value,
Yeah, okay,
probabilities.
Yes.
Okay. So we need to write it everything, correct. And that will also clarify our concept.
Yes.
Okay,
I
so
can just change
it's important to do the presentation and sometimes do some corrections.
Yes.
Immediately. It's not just after the class. Okay,
So,
all right.
Next would be step 6, Professor. So this is the estimation equation with the heteroscedasticity corrected standard errors. This is
Mhm.
just the original model so that we can
Mm.
check it easily later. So we have r squared 0.94, p-values again here, and notes again. So the easier way to get the robust results, or for the heteroscedasticity corrected values, we just change the covariance type for the
Oh.
robust covariance results.
Mhm.
There's a lot to check. There's 1 to 3, 0 to 3.
Yeah, several options.
So this one I just use C1 or
Yeah.
HC1, and the difference here is r squared is still the same, and the coefficients would still be the same
Mhm.
here. So we can see checking it with 0.04, negative 0.049 and 1.0865. It should be the same.
Mm-hmm.
But the difference would be, of course, still the standard error.
Yes.
So from 0.94, from 0.89
Mhm.
and 0.195 to 0.94 to 0.241, so they have increased.
Yeah.
But for the p-values, all of them will still be actually the same with Steve's answer.
Yeah, sure.
So this is for the HC1 covariance type. So one
Mhm.
note here is that standard errors are now robust with
Yeah,
HC1.
that's right.
We can change this actually to HC2.
Mm-hmm.
So see the standard error also changed again, but
Uh-huh.
the coefficients will be the same.
Uh-huh.
So, but we can now see that they are corrected using HC2.
Uh-huh.
So there will be changes in the standard error again
Yeah.
compared to HC1. Yeah. No, it's a different, just the different type of covariance.
There's some be- because the idea of this one is just correct the residual. So actually, they are doing some corrections inside the covariance matrix,
Yes, yes.
which is complicated.
Yes.
You know, for those engineer students, they may really understand it. For us, just forget it. Never mind. We still can use it.
Yeah. But that's just, if you want to say to the engineer, just make it good, then that will do that for you.
As long as we understand it, we know how to use it. I think the application is most important than, but for learning process,
Yes.
it's also good to go through to the math,
Mhm.
okay? But never mind.
However, Professor, I have a question.
Yes.
I tried to run again a BP test and white test with the new one,
Uh-huh.
this model, but it still shows that my probability of chi-square is still very
Still
low.
very low. Yeah.
So that means there's still heteroscedasticity in that case?
Well, this is some kind of confusion parts. If we say that we are going to use Y corrections, then we never check it again
Oh,
to
we
see whether after these corrections you still have heteroscedasticities.
Oh, this we
You
don't
know,
check it.
this is good points too. After you do the corrections, you have done something about it.
Mhm.
So just
Yeah.
just leave it there.
Okay, because I checked with this
Yeah, sure,
professor,
sure. That's good.
and I also cross-checked with eViews. It actually still has the same results.
Right.
And there is still less than
Yeah.
0.05.
Yeah.
So I tried. Oh, sorry.
Oh, you're doing factor analysis?
I just tried, Professor, since there's a lot
Okay.
of multicollinearity.
Yes.
So probably we can just squeeze that
Do
into
the
some. But,
factor
but maybe this
analysis?
is for some other.
Sure, sure.
So that's all for me.
Yeah, okay. All right. Since I didn't teach these methods in this class, so I didn't really mention. But actually, maybe we can do something about it.
I have checked that with
Yeah.
other class we had, Professor used this.
Yeah. Okay, sure. So there's two more, okay? Then Rachel, I will be the next. You'll be the next one, right? Okay. Maybe, we'll finish 20 minutes. No, both of you. Then I like to have some, time series classes, begin time series classes, okay? And we do have a holiday 2 weeks from today, right? Which is midterm exam week. We don't have class in the midterm exam week. So I like to have, some time series. Excuse me? You mean next week? Yes, there's no holidays. Holidays over up to Wednesday. The holiday is up to Wednesday, so we will have class next week, but we don't have class on midterm exam week. Okay? All right? Yeah. Data set. Oh, you want to open that? Where is it? Oh, this one? There's a data set here? I mean, our iLearnings?
In this
No, we don't have. No, we don't have the. We need to take out from iLearnings. So I'll download it. Is this the? So this is the data set, and we need to run. So this is 10, right? So this is, we're on plan 10. Okay, all right. And let me, okay. All right, so Rachel, come in here for your presentation. All right. Excuse me.
Okay, so this is my assignment, and we have 9 x variable here, and the ln price as the dependent variable. Okay, just skip it. Okay, so this is the degrees of freedom like this, and this is the equation that I have from eViews, and also I running from Gradle to see the star here, so I can see which variable that insignificant, and from this result I um, have the conclusion that the ln sailing is not is insignificant, and also the w top is insignificant too. And this one is the multicollinearity concern. We have for the ln sailing and ln cruise is 0.81, and ln cruise with fixed gear is 0.87, and ln fuel with ln horse is 0.84, and pass with ln horse is 0.86. Those four are high in absolute value, so we know that those two particular variables are quite correlated positively, that multicollinearity is a potential problem. And this is the VIF. We have these 3 high of VIF, which is ln cruise, ln horse, and fixed gear. Okay. And for step 3, I do it like Steve do, but actually I just do the plot residual from eViews, but I didn't put it here. But it show the same as the Dylan have, like the from eViews. Okay, but I forgot is it. Okay. Okay. So price. Let me see again. Do I have to do it like
We use Y first, so which is ln price.
and cruise horse?
All the variable except RESID.
Yes,
That's the
fixed
X
gear.
variable. Okay. This two. Okay. Yes. Okay. Then we have the residual. Now we have the residual. So go to the okay here. Then do the generate. Okay. Name it. Just say RESID 1. Maybe 1 equal to RESID. Okay. So we have RESID 1. This is the variable we created. Therefore, you can use that one to do the graph.
And then
Okay,
open
then
it as
open it as
equation.
a group.
Oh, no.
No. This is no. Yeah.
Yeah, residual
Then
one.
go to the view.
Choose and
Graph.
graph.
Okay. See whether we can have this one. Okay. Do the okay. This is no. This is one.
Not
This
one.
is the pass.
I think I do it
Yeah.
like the dot plot. This is the line.
Line and symbol. Okay. And this is one called box plot. Did you see that?
The one that
Okay.
just.
Yeah, the one just
Mhm.
he shows. Okay. Maybe see this one. How come you have this too? Oh, excuse me. Oh. Oh. View. And then you need to choose the verb. X verb. Symbol, right?
Is it
You need to choose, I think you need to choose X verb. Okay. How come it shows the
the residual?
the no I mean PASS. We didn't ask them to do the PASS. How come they show the PASS? Well, this is the place where we show the grass. So go and
But what I have before was I do it like this upon this equation. I don't know is it correct or not. But I have this plot. Is it the correct one?
This is the one.
Yeah. This is similar to
Yeah.
what the island have. We have dots here, which is it's kind of weird here. Okay. Yeah.
Play with all this
yeah. I will try everything with graph too. And let's continue with this one. Yeah, from what I already done, the r square is 5 blah blah blah, and the p value here is um less than 0.05, so rejected null hypothesis, hence mean the heteroscedasticity appears. And for step 4, I conduct the Bruce-Pagan test. Okay, this is my result. And for the null hypothesis, B1, 2, 3, 4, 5, 6 is equal to 0, and for the alternative hypothesis, at least one of B beta G is unequal to 0, and the R square is 38.761, and the P value for the chi-square is 0.0001 probably, and it's less than 0.05, and a rejected null hypothesis. And for the white test, I have 46 variables here, and this is the original variable is 9 and the square terms 9, so the cross product is 36. So the total of explanatory variables is 46, and it's also a rejected null hypothesis. And this is the heteroscedasticity corrected standard error models. Yeah, the coefficient and the coefficient is still the same, but the standard error, some of them are increased and some of them are decreased. And for LN sailing, LN horse, fixed gear, pass, W top, and LNH are increased, while the LN cruise, LN fuel, and 3 drag are decreased. and the compare result. Okay, so the equation seems nothing much change, so there is no significant difference when we use it. But because the number just changed slightly, and why do we bother to estimate it? Because we could know whether we have a bias or not, and whether all the variables we use are important or unimportant. Typically, the heteroscedasticity corrected standard error are larger than OLS standard errors. So um, it might produce the lower t-scores and decreasing the probability as well. And yeah, this is the what I have from the result. That's all. Thank you.
Oh, really? J, J. So she says, he says J-E. It's really romantic. And really, young generation parents name for the kids. Well, it says a young mind. Well, this is yours. This one. This one. Yeah, and make it larger. Yeah, thank you. Yeah, using
Hello. Okay, so the first step is to run the regression model. So I've used Python as well, and then compared it with the results in Gretel. So it's really the same. And then these are the comparison of expected and the resulted sign. And then is it significant? And then the interpretation based on the sign, because it's a little bit hard to understand um, the features that we have because it's about plane. So I try to search about it, and then this is the answer. Yeah, and then from the table above, the expected and resulted sign of the coefficients were the same except for the service ceiling. And then the variables which have coefficients that are significant in the expected direction at the 5% level are ln cruise, ln horse, fixed gear, ln fuel, pass, t drag, and ln age. The p-value for ln ceiling is the highest. And then for step, no, for the multicollinearity concerns, I use the correlation using heat map, visualizing it using heat map. And then we can see here that from the pairwise correlation of the variables represented by this heat map, it can be seen that there is a high positive correlation, the bright red one, between the ln cruise and ln price, ln cruise and ln fixed gear, ln cruise and ln horse, and pass and ln horse. Additionally, there is a high negative correlation between ln age and ln price. And given that the p-value of ln ceiling and w top is higher than 5% level, the results from the pairwise correlation did not support it from here. Oh, no, 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 the correlation. Ah, p-value from here. And I don't have p-value here. I just, because the could severe imperfect multicollinearity account for any coefficients being insignificant at the 5% level? And then the p-value for ln ceiling is the highest. So I check here from the correlation coefficients if it has a relationship. Yeah. Yes. But yeah, p-value, no. 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 Ooh. Mm. Mm. P-value. Oh. Mm. Ah, yeah. Oh, okay. Mm. Okay. High correlated. Okay. Yeah. Yeah. Okay. So. Mm. And then by checking the VIF, we can see here that the VIF of ln cruise, ln horse, and fixed gear exceeded the value of 5, which means that there is a severe or high correlation between their predictor variables to the other variables. And then, so here we can say that there is a multicollinearity with a given data set, maybe. And then the multicollinearity can make it more severe, the make the heteroscedasticity severe. Yeah, then this is just the explanation. And then step 3, plot the residuals. So we can see here that the vertical line, the range of the vertical line increases. So there may be heteroscedasticity here. And then step 4, conduct the BP test. So here, this one is from Python, and then this one is from, I don't know, is this Gretel? Yeah, Gretel. So we can see that the p-value here is 1.27, and it's almost near same with the p-value here. But the test statistic is 40.97, but here it's 38.76. Yeah, it's only a little bit. Oh yeah, I like Gretel because I don't have to connect to CYCU Wi-Fi. And then for the null hypothesis, homoscedasticity is present, and then alternative, it's not. And then for the Lagrange multivariate test statistic is 38.76, and its p-value is 0. Blah 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 5, but it is lower than 0.05. Then the null hypothesis can be rejected. And then conduct a white test for heteroscedasticity. So here we can see that it's same. The test statistic from Python and Gretel are the same. And then the p-value are almost the same too. Python cannot, for, oh yeah, we can see the value here in Python. And then the same, the null hypothesis and alternative hypothesis the same. And then, since the p-value is less than 0.05, the null hypothesis may be rejected. And then step 6, estimate the equation with the corrected standard error, I use this one, the HC estimators, also known as robust standard errors. And this estimator have HC0, HC1, HC2, HC3. It has 4 variants. While HC0, this one is the simplest because it is calculated by using the sample variance. Yeah, because I don't understand too. Yeah, it's a little bit hard to understand. What is HC0, HC1? Yeah, and then HC0 is the easiest one by multiplying it with the oh no multiplication using the sample variance of the residuals ignoring any dependence between the residuals. And then HC1, this one takes into account the degree of freedom in the residuals and is calculated by multiplying the sample variance by this one. I don't understand. And then HC2 is this one is similar with HC1, but it also includes a correction term for the sample size. And then HC3, this is the most complex one, and it takes into account the correlation between the residuals. So HC0 to HC3, basic one to the most complicated one. Yeah, Python. Oh, okay. Yeah, right? I don't like letters and numbers. Mm. Yeah, and then this is the result, the original one from the regression model. And then this is HC0 to HC3. And then we can see that the R squared score did not change because the R squared value only reflects the goodness of fit of the model. And then we can see here, this one is the assuming homoscedastic errors, the original one. And then HC0, HC1, HC2, HC3. So the coefficients are the same, but the standard errors, we can focus on ln seeding. It gets higher, 0.089, 0.091, 0.094, 0.095, 0.098. So the more complicated the HC estimators are, the higher the standard errors that we can get. Yeah. So the volume and sign of the coefficients remain the same, and then the CIs here gets wider. Yeah, as we use the HC0 to HC3. And then, yeah, that's all. The takeaway here is heteroscedasticity reduces the precision of the regression model's coefficient estimates. So when doing statistical inference about coefficient estimates, one should always use a heteroscedasticity consistent estimator. Yeah, if the model's error are determined to be heteroscedastic. Only that. This one is nothing. Yeah, it's from Gretel and Evius, just for comparison.
Okay, thank you for your effort. And actually, this is a good practice. All the assignments, I think, is a good practice, and also consolidate our concept of what we learn. Okay, all right. And since we have very little time, and I try to. Where's my Word file? Is here. Where's my Word file? Where's my serial correlation file? It is up here. Serial correlation. I downloaded from.
You already downloaded?
Yes, already downloaded from. Okay, I'll do it again.
No, you can click if you
Here?
already- Yeah, this one.
Yeah, I have done it. So 下载. Okay. Then.
Okay.
Oh yeah. All right. This is I'm going to talk about serial correlation, which is chapter 9. okay, which is chapter 9, we call it just serial correlation. Actually, serial correlation and autocorrelation are talking about the same thing. So this equivalent names, we usually use it in interchangeably. Okay. So we are starting to talk about time series data. So far, we're just talking about all cross-sectional data. And the difference between time series data and cross-sectional data, you can think about just the notations, okay? Before, when we use okay, okay, when we say yi equal to beta 0, beta 1, x1, beta 2, x2, beta 3, x k, epsilon, okay? And if we do this one for cross-sectional data, then I is from 1 to n, okay? Then now, the difference between cross-sectional data and time series data is the order of the cross-sectional data make no difference. So in other words, I have the data from 2022, the end of the year. This is annual data for all the listed company in Taiwan. Okay, so I will be n 1 to n, and the order of the companies really make no difference, right? Whether you're the first company or the last company, it never mind. But for time series data, if I put the t instead of I, then it come out with the time series data. Then for time series data, okay, it's really different from cross-sectional data. This cross-sectional data means the same year, but different I, means units, right? The I is from 1 to n. But time series data is the same units, so some particular units, and different years. So if I use the yearly data, so I'm going to use t from the first year to the t years. So this is the difference, okay? And I like to use in this one to sort of connect with what we learned from chapter 10 is heteroscedasticity. And now it's serial correlation, okay? Let's see the matrix. But just take a look at this matrix, okay? When we see the either from I to T, okay? If I see I, means I have this, this is residuals. The heteroscedasticity problems is related to the residuals. And serial correlation is also related to the residuals, okay? So we look at residuals, we will have all this residual, from the first one to the last one, if it is n, okay? This is E from En. So what we see, this one, how to say that, is the covariance. We see heteroscedasticity is the one from 1 to n. They have the same standard error, standard variance, right? We call it sigma square. But if they have different, means this I will, if this one means homoscedasticity, but if this one doesn't equal to this one, well, based on different I, that will be heteroscedasticity. Understand what I'm saying here? So when you look at the matrix, this is a matrix. Okay? The standard, this variance is the one here, here, is the diagonal parts. Okay? Those diagonal parts, if they do have the same standard deviation, the covariance matrix will be, with this one, will be the same. But what about serial correlation? Serial correlation is talking about this one with the second one. So it's the out of diagonals. This is called the matrix. We have triangle. This is upper triangle, this is lower triangle. The upper triangle and lower triangle is sort of this image. They're the same. So usually we just show one part of the triangle. Okay, so all this serial correlation is talking about those parts instead of these parts. Okay? All right? And usually for time series data, there are not only serial correlation, but also heteroscedasticities. Therefore, if we work with the finance data, usually we'll work with the models which deal with autocorrelations as well as heteroscedasticity. Okay, so today for chapter 9, then chapter 12 in this textbook is talking about this part first. Then I will make up all other forecasting models, especially for price assets models, which talking about this one and this one too. So understand what I'm saying here? So we talk about this heteroscedasticity. So as long as you understand this one, now we'll get to the time series data, which is talking about the correlations. And this is what we call serial correlation. Since if it is time data, it's not from 1 to n. It's from 1 to t. So it means the order of this one make difference. So you're not able to change the order of the original time series data, but you may change the order of the original cross-sectional data. So that's make difference, okay? And the other difficulty for time series data is if you use the yearly data, annual data, I mean, then all the variables, all the data generated once a year. So it's hard to get the data unless you're using, like the stock price, you have those daily data. Then you can use the data which make the data, larger. Otherwise, the data is compared with the multiple compared with the this cross-sectional data is hard to get. Okay, and also look at this one. The models to deal with time series data usually is more complex. Therefore, it's it spend more time to, and there's a lot of complicated topic in time series data. Okay, so this is the first time I think business students talking about the difference between cross-sectional data and time series data. You already know it maybe. All right, and okay, so again, when we're talking about the serial correlations and autocorrelations, we're talking about pure, when we talk about heteroscedasticity problem, we also say it's pure. What do we mean by pure? Means the specified model is already correctly specified. Means that there's no omitted variables, there's no functional errors. Okay? This is what we get correctly specified. We can solve this problem of autocorrelation or heteroscedasticities. First, make the model correctly first in order to solve heteroscedasticity problems as well as autocorrelations problems. So if you have some other impure, problem, something like omitted variable or misspecification, then it looks like a zero correlation problems or heteroscedasticity problems. Actually, is not. Okay, actually, it's not. Okay, so here we're talking about really true zero correlation problems. Okay, and the most common zero. Now look at this one. So we are talking about this notation. We're not talking about all of them. Okay, this one. Okay, so I'm going to talk about this one is epsilon t. Okay, let me see. The most common version or model of the autocorrelation is what we call first order. So what do we mean by first order? If you take looks the textbook, and it shows that epsilon t is equal to rho epsilon t minus 1. And what's the notation in our textbook? I'm using, okay, ut, okay? And, if this is for all meet the OLS classical assumptions, means E epsilon t is distributed as IID, individually independent. Then this is what we call IID. Okay, and usually there's a mean is equal to 0, then the standard deviation is equal to something, which is there's no zero correlation. Okay, but if we have zero correlations, means that the epsilon t is related to the previous period, so t minus 1. And this is called serial correlation coefficient. Okay, this one. And this is what we call first order, means just related to t minus 1. First order. Is there any other order? Yes. If I have this one, rho 1, t minus 1, rho 2, t minus 2, ut. This is the second order, means the current error terms, residual error terms, not only related to the previous one, but also previous 2. Okay? So this is called second order. And this is first order. And some of the residuals have seasonal effect. Seasonal effect means what? Repeat every season. So what is this? It becomes to t minus what? 3, 4. Seasonal. Season we have 4 seasons every 3 months, right? So this means it's 1 or 3. The current is 4, right? Right? The if this is after 3 months, this is the 4th month. So this one. So if we have this one, we call it seasonal order. So I want to say is not only the first order, but also different orders. And usually we call this one is lag. So this is called lag 1. The previous -1 is called lag 1. This is called lag 2. Okay? Okay, all these terms, we have to know exactly the meaning of that. And also, since this is a zero correlation coefficient, okay, what is the range of this one? We know the correlation coefficient before. Then we do have this correlation coefficient, right? Then what's the range? We call this R is the correlation coefficient. So this one is -1 to +1. Okay, what about this? Yeah, it's pretty similar. So this one is also between -1 and +1. And usually, do you think why it cannot be greater than 1? Any, just very intuitive thinking. If the correlation greater than 1, what does that mean? Do I put this one as? This means the current error terms. This is there's a relationship with this one, and this one is related to the past periods. Then, if this one is greater than 1, what does that mean? Not only very correlated, but also, something like this one. Is any diagram here? If this is -1, this is t, then what's the diagram looks like? This is not probability. It's more than 1. What does that mean? Means the current related to the past one and even bigger. So, just like this one exploded. Just exploded.
Wait, so that's possible?
That is not possible, right? That is not possible. Therefore, it won't be greater than 1. So it's smaller than 1. Okay? So if it is since we have positive and negative, right? Between 0 means there's no zero correlation. 0 means if this is 0 means the first one, the present doesn't relate it to the previous one. So we can divide it as a positive relationship and this is negative relationship. Negative correlation means a lot, or negative correlation means a lot. When we say positive means, if I say it is 0.6, suppose. This is between 0 and 1, right? And it's close to 1 part, this size. Not that close. So if I say 0.6, means whatever now will be related 60% of the previous periods. Okay, so the higher means the current related to the previous one is higher. Okay, so you know, maybe you can become 1 at most. Okay, means the current is exactly the same as the previous one. And what about the negative? Multicollinearity. Well, remember, when we say multicollinearity, always talk about the x variables. Now we are talking about residuals. So no multicollinearity terms here. No, no. Heteroscedasticity and serial correlation is about this. Okay? You need, have very correct concept. Multicollinearity on deal with these parts. Then, yeah, and the correlation is among this one. But heteroscedasticity is this. Serial correlation is also this. Okay? And heteroscedasticity can be cross-sectional as well as time series. But most of the time, cross-sectional data occurs heteroscedasticity problem, but not really time series. But serial correlation always happen to time series data, not cross-sectional data. And time series data also have the problem with heteroscedasticity. You mean this is 1? Yeah, we'll talk about that later on, but it can be 1. It can be 1. Okay? Then I'm talking about the negative side now. What about the negative side? Okay, what do you see the diagram if it is a positive? I mean the diagram of the E residuals. Yes, so you can see the diagram from our textbook, okay? On 295, figure 9.1. If you see the diagram, okay, this is what we call positive zero correlation graph. Look less. It can be like this one. It can be like this one. Means what? If I have the first one here, then since it is positive, so is all on the positive side. This is 0, right? This is 0 line. So I would have positive for the 0 periods. Then go down, 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 down to the negative side and still have positive still correlations, so still on the negative signs. Then gradually come up to the positive. So this is positive zero correlation, one possibilities. And this is one too. Oh, let's see the negative, okay? Negative means on the figure 9.3 means like zigzag. Positive, negative, positive, negative, positive, negative means negative correlations. Now I'm in positive, but immediately jump to the negative, then go back to the positive and negative. But if you gradually go up, gradually coming down, this is positive correlation. Make your concept correctly. Okay? All right? See the pictures. And if you don't have any correlations, just like the pictures on the 9.2, really randomly. Sometimes, positive, negative, but not those zigzag. Okay? And I will say that most applications, most of the applications occur those positive zero correlations more than the negative one. Okay, so this one will be more reasonable in the real world. So most of the time when we talk about the zero correlations, we really talk about positive situations. Okay? All right? I think this is just the general introduction of what we say. Okay, let me just stop here, okay? And next time, I'm going to talk about the consequences of zero correlations. Okay, and I hope I can finish. I hope I can finish chapter 9 next time. I hope so. I don't know. And in order to have the assignments due, although we don't have a class on midterm week, but we can have assignments due. You can turn it in on exam week. Okay, I'll see how far I can go next week. All right? Okay? All right. Thank you very much. I'll put this one.